Are we ready to go?
Let's go.
Great. Let's see. Greetings, everyone. Good morning, good afternoon, good evening, as appropriate for your longitude. We welcome you to the second Punch Science meeting, and thank you for your interest and participation. We understand we have people from all over the globe who are attending today, over 100 participants. I'm Dr. Sherilyn Morrow. I'm the Outreach Director for the Punch mission, and I'm pleased to serve as co-chair of this first session with Dr. Amir Kaspi of the Southwest Research Institute. We will be your timekeepers and the collectors of your scientific questions. And to help us keep on track with our very full agenda, we'll signal you about 2 minutes before the end of your talk, and then end promptly at your finishing time. So let's see, throughout the day, there will be reminders and tech support from our technical facilitator, Kelvin, for using Slido to pose your scientific questions as the talks proceed. I need to emphasize that we won't be taking questions right after the talks, and instead collecting questions on Slido in preparation for the ensuing discussion and session. So Slido is another program outside the Zoom chat. It will permit the intellectual exchange of our meeting to be documented in a cleaner, more effective manner. A link to Slido has been provided on the opening slide, and so we strongly encourage you to go there and register so that you can record your questions as the speakers proceed. Also, there's a very brief feedback survey available that will allow you to post your feedback on the structure and content of this meeting, and that will also be posted in the Zoom chat. And if you ever want to have that, please go ahead and make a request in the Zoom chat, and we'll be pleased to send you that link as well. So without further ado, I'd like to introduce to you the principal investigator of the Punch mission, Dr. Craig DeForest of the Southwest Research Institute. Craig?
There we go. All right, so I did the first unmuting gaffe of the day. Everybody else can feel relaxed about it. Welcome. I'm really glad to have everybody here. We've been working on this mission for a long time, and this is our largest science meeting yet. As Sherilyn pointed out, we have participants from every continent except Antarctica. So give yourselves a hand, and I apologize for the odd times for some of you. So I'm going to give you a quick overview of the mission and where we are. Basically the who, what, where, when, why, and how, not in that order, of the mission. And then I'll hand off to Sarah Gibson, our project scientist, who will describe give you a reminder overview of the science, and then we'll move into the details of the sessions. Most of this, as Dr. Morrow pointed out, most of this meeting will be in a Shine style discussion with scene setting talks, and we have a great agenda for you, so I'm really thrilled about it. So what is Punch? Well, this is a reminder. Most of us know what it is, but Punch is a mission to understand the connections between the sun's corona and the heliosphere, how the corona gives rise to the heliosphere and solar wind. We're doing that by making 3D images of the corona and of the inner heliosphere. We do that in 3D using polarization, the physics of polarization in Thomson scattering. We use 4 synchronous satellites to do it. And when I say synchronous, I mean they're operated synchronously to within about a second, even though they're spread around the world. We'll talk more about that soon. It's a 2-year mission starting in about late 23. So why Punch? Well, for most of my career, the fields of solar physics and solar wind physics have been separated by the technologies that we use to carry them out. On the left, you have a representative set of images from the SOHO-LASCO instrument. These are images of the solar corona as it evolves. On the right, you have something representative of heliospheric physics, which is a series of traces of physical parameters of the wind as it sweeps over a spacecraft. And so there are other missions right now that are starting to unify these fields. In particular, Solar Probe is flying through the solar corona and bringing the solar wind science into the corona itself. PUNCH goes the other way. We're bringing the science of solar imaging out to image the solar wind itself in detail as it forms. This allows us to determine cross-scale physics and a variety of things that are hard for in situ instruments to capture. So imaging and in situ measurement are very complementary. As far as why we're here now, the purpose of these meetings at this point is to understand how the field is advancing as we prepare for PUNCH launch. That's about 2 years away, a little over. We want to make the best use possible of PUNCH data when they become available. So we're developing ideas for investigations in addition to the prime science. We're investigating the tools that we need to carry out the prime science, and we're designing data products to make PUNCH more accessible to everybody. So we want to welcome both the funded team, the folks that we named to NASA in the proposal, and also the broader community to work on science together. I feel very strongly about this, that missions that are successful are those missions that really build a community. And we want to reach out into the science community and also to some extent into the broader public community to make sure that everybody can work together on the data that we'll be producing and join this voyage of discovery. All right, so let's see. Next is where does PUNCH go? It goes to 500 or 600 kilometer altitude orbit. We launch on a single spacecraft. This is notional here. We haven't determined the launch vehicle yet. We deploy the 4 spacecraft individually with spring release at a couple of meters per second. It turns out if you never stop moving, a couple of meters per second is enough to get you around the world in 90 days or so, or a third of the way around. So right after launch, the solar panels deploy, you just saw that. And shortly after deployment from the launch vehicle, the spacecraft are all close together, but because they've deployed in slightly different directions, they drift apart over time. You can see the time advancing during the commissioning phase. About 30 days in, everything's outgassed enough that we can open the protective doors on the instruments. This is a wide field imager, and this is the narrow field imager. I'll talk about these in just a moment, how they work together. Then once they're open and we finish commissioning the instruments, then over the remaining 60 days of the commissioning period, they separate out to be on station 120 degrees apart in orbit. We have small rockets on board that both station keep and stop the drift at the beginning of the mission, so that the 3 wide field imagers are 120 degrees apart. Now, as the spacecraft orbit, every 30 degrees of orbit, they rotate 30 degrees to keep the Earth below the plane of the baffle for these wide field imagers. So the fields of view all extend out from the Earth onto the celestial sphere and work together. So the 3 wide field imagers are constrained to be 120 degrees apart. The narrow field imager sees the entire inner portion of the field of view and is unconstrained in its orbit. How does this work? This is another view. This is the view of the constellation on the left here against the star field. All of these different instruments work together to produce a single virtual instrument with a 90-degree wide field of view on the sky. So we're seeing everything from about 1 degree from the sun out to 45 degrees from the sun. And you'll notice that this heartbeat that you see, that pulsing, is the 4-minute cadence of the observatories as they orbit the Earth and paint this large field of view on the sky. They're synchronized and the fields of view overlap so that we can produce a seamless data product that merges all of the fields of view into a single large virtual instrument plane. Over on the right, you can see where the spacecraft are in orbit. They're right over the terminator line in a sun-synchronous orbit. So the data products that you get, you can either look at the individual frames coming from the observatories, or, and this is what I think most people will look at, you can look at the mosaics that we produce in the operations center, which produce a single unified field of view. All right, how is PUNCH progressing? Well, this is our schedule summary, and this is where we are. Phase A is is concept design. Phase B is preliminary design. Phase C, which is merged with the next phase, is comprehensive or final design. D is assembly, integration, and test. E is operations. So you can see we're already about halfway to launch, a little over halfway to launch from phase A. And of course, if you count the time for the proposal, which started in 2016, we're about 2/3 of the way to launch. We were impacted a little bit by COVID-19 and our schedule that stretched out our phase B a bit. That's all been taken care of. We had PDR in May. We were successful at that. And we just finished our KDP, or Key Decision Point C, which allows us to progress into final design and development. So very excited about that. The phase E start date is 90 days after launch. Our launch readiness date, that's that LRD, is in October of 23. We don't actually have a launch vehicle picked out yet, and so launch may be a little bit later. We don't know. It depends on the rideshare arrangements that NASA is able to make with other missions. And let's see, here we go. These are just some beauty pictures of things that have been going on. We have a lot of development on the spacecraft as well. These are sort of parts and data from some of the instruments. Over on the left, you see a polarizing filter wheel, beautiful work from the Naval Research Laboratory. NRL also have been refining their design for the narrow field imager, which matches the SOHO LASCO field of view that I showed at the very beginning. That's a proto-flight instrument. They're going straight to flight, so they don't have an instrument built yet. As we move around the bottom here, you can see the wide field imager. We have an engineering model that's been built and tested. The inset. Hello, thank you. The inset optics there are from Teleview, and you can see that inside the instrument. And over on the right is an image taken through the instrument of the inside of NRL's vacuum stray light test chamber, Scotch, demonstrating that the baffle is actually attenuating sunlight by at least 17 orders of magnitude in that very small space. I'm excited about that. And of course, no set of baby pictures would be complete without Nick Waltham's first gnome light image. He always photographs gnomes, and as you can see, the gnomes were wearing masks because of COVID. So that's the first light that was taken through the PUNCH cameras. All right, who can be involved with PUNCH? You. Our intent is to build and support a robust community beyond just the initial team. And to that end, we have an open data policy and open science team meetings. So if you're here now, you're either part of the initial science team or part of the broader community that we're trying to merge into the PUNCH science effort. So thank you for coming. We have an open data policy, meaning that every data product that we produce is released to everybody at the same time that it goes to the team. There's no proprietary period. We're planning workshops on how to interpret the data. There are some nuances. Data are surprisingly counterintuitive. Imaging data are surprisingly counterintuitive. And so we want to make sure everyone's aware of the pitfalls and the tricks that you need in order to interpret even the prepared data. We have a robust outreach program to the broader community to help bring students in at all levels and help feed the pipeline for more science activity moving forward. And of course, if you want to get involved, talk with a working group lead. They're speaking throughout the week to introduce their sessions. You can talk with Sarah or with me and find out how to get involved. Or you can participate in discussions here and at upcoming meetings, which will be announced in the usual places. So when is launch, and more immediately, when is lunch?
Craig, we are a little over time, just so you know.
Excellent. This is my last slide. Our launch readiness date is 3 October of 23. I think I mentioned that. We may launch a little bit later, but we may launch very close to that time. Lunch is more immediate. Because we're in so many time zones, we don't have a separate scheduled lunch. So I apologize for that, but please do come to the icebreaker right after the sessions end. I think there's a short break, and then we come right back. I will now hand off to Sarah Gibson. Please put any questions in Slido. I'll be glad to answer them.
Okay, thank you very much, Craig. You got my screen? So yes, welcome everybody. It's wonderful to have you all here. And in the next few minutes, I'm not even going to attempt to give you like a full science update. Luckily that we have 3 days to do that. In fact, it's the central purpose of this meeting. So what I am going to try to do in the next few minutes is to quickly describe this and the other motivations for the meeting. So to remind you with the help of the agenda of our overarching goals and objectives and how they map to our working groups. And then I'll briefly overview how the meeting will be highlighting what's being done to develop the tools for PUNCH data exploitation that Craig talked about, both within our team and in related community research. And then finally, I'll point to some of the efforts to extend to the reach of PUNCH science through building and training the broadest possible PUNCH community. So first of all, PUNCH's primary science goal is to comprehend the cross-scale physical processes of heliophysics. And by cross-scale, I mean from microscale turbulence to the evolution of global scale structures. Our purpose in doing so is to unify the solar corona and heliosphere, as Craig said, and in particular to go from the outer corona to the inner heliosphere, which is a region that we call the young solar wind. PUNCH has 6 science objectives that span both the quiescent and the dynamic young solar wind. And we achieve these by activities of 6 working groups. And in this meeting, we're combining them into 3 supergroups. The first supergroup is led by the dynamic duo of Barbara Thompson and Nikki Weil. And it maps the quiescent or non-erupting global solar wind flow and asks the question, where and how do microstructures and turbulence form in the solar wind? Barbara and Nikki will be bringing you all up to speed about what their working groups are about. And then we're going to hear scene setting talks from Heather Elliott and Alida Higginson. And then tomorrow, on Tuesday, Steve Cranmer and Kurt de Koning are going to team up to highlight the science of the Alphane surface or zone and about the formation and dynamic evolution of co-rotating interaction regions. And we have Rohit Chiber and Vic Pizzo to set the scene on these mysterious topics. And finally, on Wednesday, Anna Malinishenko and Mihir Desai are going to join forces and introduce the always popular topics of coronal mass ejections and shock dynamics and morphology. And we have Angelos Furlidas and Joe Giacalone to set the scene. The rest of the meeting, as Craig commented, is going to be discussion heavy with Shine style presentations and discussions on our ongoing efforts to develop the tools we need because we want to hit the ground running when PUNCH launches. And we're also going to have, as you can see, plenary free discussion where we can dig deeper into the issues raised by your questions that you're submitting to Slido. The intention is to extend the reach and impact of PUNCH science by trying to get your ground floor input into our planning process. Now, making the meeting public, as Craig said, is part of our commitment to engaging scientists and public alike. And we're going to have talks that describe what we're doing, efforts there. We'll be having Sherilyn Morrow, this session's chair, who is leading our Vibrant Outreach program. And we're going to have a presentation on the awesome activities of the next generation of space researchers working with PUNCH type data and our associated instrument, the STEAM, Student Thermal Energetic Activity Module, that is riding along with PUNCH. Now, building a community means also connecting with the up and coming researchers already in our field. And to that end, we have instituted an associate investigator program, which is a way of forming a cadre of early career researchers who are working on questions that support and enhance the PUNCH mission science. So on Tuesday and Wednesday mornings, we're going to be proud to highlight the science that Rafael Atier, Bea Gallardo-Lacourt, Chris Gilly, and Elena Provornikova, our first set of PUNCH associate investigators, are going to be talking about. And lastly, for PUNCH to be a success, we have to do more than just provide amazing data. We need to build the community of PUNCH users. And to that end, we're going to be sharing our plans for the Science Operations Center and describe how PUNCH fits into the NASA Heliophysics System Observatory Connect program. So this is how you're going to get your data, what the data are going to look like, and what we know so far about how we're going to use it. We're building the tools, the analysis tools now, but ultimately we want this broad community of user. And so we want to engage and build and ultimately train a community of users and scientists throughout the world. By doing so, the sky is the limit for the amazing science that can come out of PUNCH. You can see we've got three woofies in the Nuffy here flying along with the dragons. Okay, one final thing, we're having an icebreaker activity this afternoon, and we encourage you to join us for a fun adventure organized by Barbara Thompson, and we will have prizes. The festivities begin about a half hour after the science part of the meeting, so please stick around and join us for that.
Great, Sarah, thank you so much. Thank you both, Craig and Sarah. We're going to move right along to a presentation, a duo, a dynamic duo to speak about Working Group 1A, the Global Evolving Solar Wind. And we have Barbara Thompson to lead us off with that, who will introduce Dr. Heather Elliott, whose presentation will be about solar wind statistical relationships useful for providing analysis constraints and additional space weather data products. Go right ahead, Barbara.
All right, can you see everything and hear me okay?
I hear you. I don't see your screen. It says you're sharing, but there's not a slide.
Weird. All right, let me try again.
Yeah, we don't see it yet. Barbara, try sharing your entire screen instead of just.
I already did. It doesn't show up?
No, it doesn't. I do have your presentation pulled up here, though. I can share for you if you like.
All right, well, let me just try one more time. What I will do is I will share the specific presentation and see if that works. Do you see anything?
Yep.
Yes.
Okay, great. Weird. Okay, so it didn't allow me to do the full screen. Thanks, everyone. So welcome to the PUNCH meeting. We're so glad you're here. As Sarah and Craig were describing, PUNCH's science goal is overall to really understand the cross-scale physical processes from microscale to the evolution of global scale structures that unify the solar corona and heliosphere. And our working groups and our science goals are broken up kind of into two areas. One is the ambient solar wind, basically the structures that make up the solar wind in a quasi-static or a large-scale sense. And then the second group is the dynamic solar wind, coronal mass ejections, CIRs, and shocks. And Working Group 1A is the group that I'm going to talk about right now, which is how does the young solar wind flow and evolve on global scales. Now, for the first time ever, PUNCH is going to quantify the day-to-day global evolution of the ambient solar wind flow. And we know we can do this because there has been test campaigns like the Stereo Core 2 Deep Exposure campaign, which reveals that there is visible flow happening everywhere we look. So the wind speed can be traced using these small features in the corona and the heliosphere. And the goal of Working Group 1A is to take these flow structures and turn them into the global properties of the solar wind. So the ambient solar wind is roughly bimodal. It's fast and slow streams, and we know from from previous observations that it's possible to view both and track the flow in both. And so our goal is to understand how these coronal structures and boundaries relate to the solar wind characteristics and solve outstanding problems that require these global properties. So our science activities for the first PUNCH working group is we focus on measuring the time-dependent solar wind flow from the outer corona to the inner heliosphere. And so we want to identify these changing boundaries between the fast and slow solar wind. We want to determine the large-scale flow context for these measurements that we're going to connect to in situ and provide the ground truth for verification for global simulations. Our scene setting talk by Heather Elliott will talk about how this is possible and why there's so much important science to be done with this. Another goal is to characterize the global solar wind conditions through which the transient structures propagate. So the first science objective 1 of PUNCH is really setting the stage for science objective 2, because if we understand the global properties of the solar wind, then we have a better understanding of how the transients take place, because none of these transients happen in isolation. They are all in interaction with the global solar wind. You'll hear a talk from Dan Seaton later on that details the data products that we'll be delivering and for all the different areas, and also the plans for the PUNCH data center. So, but we want to really stress that the PUNCH science requirements and our data products are the starting point for PUNCH science. We believe that the best science to come out of PUNCH is probably not been defined yet. We are going to do some excellent science, but there are a lot of breakthrough capabilities because of the way that PUNCH is going to be delivering new types of data that people have not been able to work with in the past. And so instead of, we have the regular PUNCH data products, and we've identified some what we call extended science measurement targets. These are ways that we can measure properties in the PUNCH data, measurement targets that will bring us a lot more vital information about the ambient and the dynamic transient solar wind. So I'm not going to go into this too much detail. This presentation will be available to you later on, but there are 4 general measurement targets. One is to, rather than just simply come up with some global properties, we would like to really do a good job measuring the velocity versus the latitude and the radius on global scales, which means that instead of just radial properties, we know that the solar wind doesn't flow out fully radially, and the non-radial structure is a very important part of understanding the development of the inner heliosphere. And so we would like to understand the non-radial properties. We would like to understand the 3D structure. And we also know that because we are getting most of the, we're integrating through the image plane, there are going to be multi-line of sight features. And so we're going to try to identify methods that can help separate and understand multiple features along our line of sight. We would also like to measure the velocity versus latitude on small scales to understand shears and compression regions and relate them to these density structures. This becomes very vital for moving into our understanding of turbulent flow, the development of flocculation, and the development of the Alphane zone. We also would like to understand the relationship between these small flows, global flows, and these large structures that are going to be addressed in Working Group 2, like CMEs and shocks and large co-rotating interaction regions. And so, and this is sometimes a different goal, because measuring a small scale steady flows versus large structures can sometimes the methods need to be adapted for that. Finally, we definitely want to nail down the Alphane zone and really do a good job of understanding the development of that transition to real heliospheric solar wind. We want to be able to understand not just outward flows, but inward flows in waves, which characterize that Alphane limit. And and all of these do relate to the different science objectives that we have. I have a rough mapping of the different new extended science measurement targets and how they would map to help us really address the PUNCH core science goals. Now, there's a problem, which is that this is hard, and it's not really been done very well before or at all. And so for this reason, PUNCH has formed the Flow Tracking Working Group, which is to make progress towards really turning PUNCH into a velocity meter for the entire heliosphere, or at least the heliosphere to 180 solar radii. And what we'd like to do is, but we needed people to work on that. There have been 2 workshops so far. They've been working on advancing our ability to identify and track flows in coronal imagery, to understand the methods, that are in the current state of the art to understand how we could prepare them for PUNCH data before PUNCH is launched, so we're ready to go, and how to optimize them for model interpretation. So you're going to hear a summary from Raphael Atier and Bay Gallardo Lacorte of the most recent flow tracking group's activities. And you'll also hear several talks highlighting the progress in flow tracking methods. The flow tracking group is made up of a lot of people from the community. You'll hear some of the information that people are going to be trying to derive from PUNCH data. But we welcome all talented scientists. We welcome all interested people because, again, the best of PUNCH is to come. And no mission is happy with just simply doing what we did before better. We'd really like to open up new science questions and really make sure that PUNCH can do, we take the most opportunity of PUNCH. So as you learn about the other PUNCH working groups and our science goals, we invite you to consider what this wealth of new and unique data can do for your science and the questions that you're interested in. And I would like to, I'm very thrilled that Heather Elliott was willing to give our scene setting talk. We challenged Heather to really think outside of the standard, the science goals for PUNCH and help us understand how to derive exciting scientific advances that take full advantage of PUNCH's capabilities. And so with that, I'd like to introduce Heather Elliott and a presentation that she and also with Nadi Alzate worked on, which is going to help I hope will really inspire you to think of all the capabilities and all the science that PUNCH can do. So I will hand it off to Heather, and I think Heather, are you ready to go? I can see your screen. Awesome.
Okay, yeah, let me go into full screen.
Heather, I will give you a 5-minute warning.
Okay. All right. So as I mentioned, I'm going to look at what we can get out of using SolarWind statistics. So I have kind of two main objectives, is looking at using SolarWind statistics to constrain like image inversions, models and assimilations, particularly for the background wind. And then using SolarWind statistics to derive additional forecasting quantities like the other solar wind quantities, IMF and geophysical indices. And to give a little bit of background, when you look at the solar wind at 1 AU, you get you get a combination of source properties and changes that have happened to the solar wind parameters en route as you go from the sun outward. As we all know, that the sun has regions that emits fast wind and regions that emit slow wind. And since the sun rotates, you can have a fast wind region emitted after a slow wind region, and then it catches up to it and you can form a compression. And on the opposite, on the backside, you can get a rarefaction. And for the background wind, typically what we think of the background wind as the material from the coronal holes, and the slow wind and the co-rotating interactions, these compression regions that are on this diagram by Vic Pizzo. But also the fast wind, it can be faster when it's coming from a polocoronal hole or polocoronal hole extension. And the larger the coronal hole, often the faster it is. And then also in the center of the coronal hole, it tends to be faster, and on the edges, it tends to be slower. So even the background wind has a lot of variation in speed, and the CMEs have a wide range of speeds too, but even the background wind is quite variable. Okay. All right. So this is a superposed epoch of analysis of 27 CIRs. The black curve is the solar wind speed. So this is showing an average of 27 different transitions going from slow wind into fast wind. And at the speed transition, that's where you're in the co-rotating interaction region. And the red curve is density, and you see that it peaks slightly before the steepest part of the rise. And so what these 27 events, they're kind of stacked where you get the steepest rise, which is where you get the changes in the flow direction there. And another thing to note is that the density, the field strength of the IMF, it seems to be peaked centered on the steepest part of the rise. And in the slow wind and in the pure fast wind, it has a similar field strength. So the magnetic field strength captures a lot of the dynamic interaction. And so you really see the compressions stand out in the IMF field strength. And the density is piled up a little bit ahead. But one key thing to note is that for the temperature, the slow wind has a low proton temperature at 1 AU, and it has a high, and the fast wind has a high temperature, and then it's even highest in the compression region. So in particular, you really see the combined effects of source and dynamic interaction for temperature. You see a lot more of the dynamic interaction in the magnetic field strength, and you see a little bit more dynamic interaction in the density than you do see source properties, but there's also some source aspect that because the slow wind tends to be, the pure slow wind tends to be slightly higher dense proton density than the fast wind. And so the field strength is a really good one that captures the dynamic interaction. And so this is going to come up again. Okay, so a long time ago, I had decided, well, it might be a good idea to look at how steeply the solar wind speed rises and falls. So this is just solar wind speed on the left as a function of time. And I just had a 2-day window, and I slid the window across these 1 hour sets of 1 hour measurements. And I calculated how steep the slope, the speed time slope was. And when it rose, had a steepness above a given threshold, when it was rising, it's colored orange. And then when it's falling below that same level of threshold, it's labeled as rarefaction. And I use this to sort the data. And in particular, I did this looking at the temperature speed relationship in the solar wind. And on the right, I have just what the temperature, the color coding is the number of samples that have a given temperature and speed at different spacecraft. The first panel is Helios, and then ACE, and then Ulysses. And then it's the same data sorted by whether it was rising or falling, and then just doing 1D binning instead of 2D binning. And I get, what I see is that as you move further out, the rising times tend to be hotter, which is what you would expect for a compression region. But you can see by the time you get to 1 AU, there is a real impact of dynamics. And so doing this kind of sorting can help you focus in on some aspects of the dynamic interaction that happen en route. And if you look at, so pretty much no matter where you are in the heliosphere, the density of the solar wind tends to be decreasing as you move further away from the sun. And it basically tends to decrease at about the spherical expansion rate, which would give you an R⁻² trend. And so whether you're in the times that are rising, which would be associated with compression, or whether they're decreasing with rarefaction, it's still pretty close to the -2. And so I did some statistics in 2012 that show this, that whether you're in compression or rarefaction, it's just slightly different. And but some of the spread that happens as you go from closer to the sun to further away from the sun, that spread increases as you move further away, and you get the spread is coming from in the range of densities, in addition is related to whether it's compression or rarefaction, but there's still this overall pretty much spherical expansion R⁻² trend. And you even see in the outer heliosphere, it's still pretty close to R⁻². And so this is key because this is used a lot as a constraint. And it's a pretty good one. But when it's deviating from it, it tends to be related to the dynamic interaction. Okay. And so I've been updating my work on temperature versus speed. These are some new results where I did some separating, doing different curves for compressions and rarefactions, and also just times when the slope was small. But the temperature speed relationship for the background one, here I've removed the ICMEs, is very linear. So this arc shape it's a linear fit because a line on a semi-log plot has this curved shape to it. But I've also done analysis looking at the density versus the solar wind speed, and it's better fit with a power law relationship. But again, you get the spread is related to this, whether it's rising or falling or in a compression or a rarefaction. So, but these are all relationships that we can utilize because we measure, we're going to be measuring the flow speed is going to be one of our strongest quantities that we measure, which is a key point. If the flow tracking, the better we can do the flow tracking, especially for the background wind, which Barbara brought up, that these smaller features, if we can track those and get like what the flow is in the slow wind and the fast wind, we have a lot of leverage here. Okay. So, but I would like to point out, there is a caution to this, that some quantities, even if you have a radial trend in them, like the density has a radial trend, the R component of the IMF has a radial trend in it. There's also a time variation and on here, the relevant curves are the red and the blue, which are in the ecliptic at 1 AU. This figure also had some Ulysses data in it, but the thing to note is that there are these long-term trends that you see, like you see the number flux, which is just the density times the speed, has this kind of long decrease over this time period, and also so does the magnetic field strength, and a lot of that's coming from the trend in the radial field. Here, there are some long-term trends that kind of come and go in the radial field, which then it changes the magnetic flux. And but if you a lot of times when people do expansion factor or no, sorry, when a lot of times when people do source surface mapping and you get the radial field close to the sun, then you do like an R squared drop off. And so there's a radial trend in R, and there's one in B, and then there's one in the density, and then the number flux, because and then the speed is on average constant. So the number flux is tracking the trend in the density. Okay. And so a thing to note is that, remember I told you there was a trend in the magnetic field strength as a function of time, and that the field strength peaked at the steepest part of the rise. So what I did here is I took the magnetic field strength and I divided by what the magnetic field strength was for the previous solar rotation. So I basically have normalized out any long-term trends. And so you can use this in forecast mode. And what you see is that there is a pretty strong relationship between the field strength divided by the field strength for the previous rotation, which you'll always know because you'll always know the previous solar rotation. When I did this, and I didn't divide by the previous rotation, it wasn't as good a correlation. And then here I also did some separation between whether it was rising or falling here, and just did a separate, got two slightly different slopes for either side of this. But this is the 2-day window, and I look at how steeply the speed rises and falls in this window. So remember, since the field strength peaked as it was rising, you can really pick up this trend with an equation with equations like this. And so here's when people use they often use like WSA or source surface model, and they get the radial field strength, and then they map it out. There is an R squared drop off, which early on in the 70s was established, but now Orbiter and Probe are getting new data on this. they when they compare with 1AU, they always have to include this factor of 2, which is not fully understood yet. Linker has a paper on this issue, but you can add this systematic offset in, and you get a better agreement. Some other common things is that the solar wind tends to be on a Parker spiral, and you can use this information to get you tangential field, and you already know the radial field if you use the source service mapping. And then in order to, since I get compression effects on my magnetic field strength, you get these little wiggles in the radial component and the tangential component that have to do whether you're in a compression or rarefaction. So I just took kind of like a percentage of that variation and added that in. And then also you can determine, and then you can solve for the magnitude, but you don't know the sign for BN or BZ that you get if you do a coordinate transformation, but you can get an estimate of the sign because the tilt of the Earth's dipole, it changes systematically, because on average BN is 0 in the solar wind. It's just these small fluctuations about 0 all the time. But it's the tilt of the dipole, because in the GSM coordinates, you're aligning with Earth's dipole that really tend to give you the sign on BZ. And then there, you can create a map of of IMF BZ as a function of the time of day and the day of year. And there are these systematic trends in that, and you can pull the sign off a BZ, or you could even just do a lookup table off of this as well to get BZ straight. And then some other relationships that are ones that would be very valuable for PUNCH mission is that if you look at the KP index, and so I'm color coding the KP index on these plots, and I got the solar wind proton density versus the solar wind speed. And there's a systematic trend in the KP geomagnetic index such that at low densities and low speeds, the KP is low, and then at higher densities and higher speeds, the KP is higher. And it's very systematic. And since we're going to be measuring the flow speed very well, and hopefully from the polarization, you could also look at the density, get a density estimate, or from the speed profile, you could get a density estimate. And okay. And so you can, and this works for CMEs or the background wind, you can estimate KP if you know the density and the speed, or if you know how steeply the speed rises. And so I've looked at applying these statistics to output from Wang Shili RG, and the speed is depending on the expansion factor and the angle to the coronal hole boundary. That and they get that by using the source surface model to get the amount of bending for the expansion factor, and then the separation angle from the foot point of the line they're on to the coronal hole boundary is this D angle. And so what I discovered is that I'm right here, I'm plotting the difference between the model and the data, the WSA output and the data, and there were systematic errors. And so I've started correcting for the systematic errors in expansion factor, angle to the boundary space. And here I broke it out differently. I just did angle to the boundary versus speed and expansion factor versus speed. And what you see is that yes, I am getting an improvement when I do this, use this array to do a correction, and it's optimized in this space, so that's why you get 0. But however, at a given expansion factor, I'm averaging over some positive and negative errors, and so it looks better than you in this space. But there still are some residual errors, but they are improved. But when I do these correction, it gives me a better estimate for the speed. And and the speed profile as a function of time, then I can, if I have a good estimate of the whole speed profile as a function of time, I can start applying those equations and do forecasting. And so this is relevant to PUNCH, because if we're measuring the flow speed, we can get the flow speed as a function of time in the direction of what's headed towards Earth, then we can start applying these equations. And so this is just showing you the model speed versus the measure speed. And it's just showing that when I do the corrections, it works a lot better. And so you get more points along the diagonal of perfect agreement in there, and you get a more symmetric distribution, and it's a more narrow distribution. So the error is improved. And these are the results I get when I apply all those equations. And so, and it does well in the background wind because, you know, the WSA is predicting the background wind speed. When I apply these equations, I get a lot of the same variations of the density and the second panel from the top, the temperature, and then also I did a lookup for the KP index. I'd use my density estimate and my speed estimate from those equations to then look up the value for the KP index. And then also this is what you get for the different components of the IMF. I put the speed again for reference. And then this is the BR and the BX component of the solar wind. And those little wiggles were coming from me applying a little percentage from the magnitude to get the compression effect. So those little wiggles are the compression effect and rarefactions in there. And then as you see what I'm talking about, that BN tends to be close average to 0. But then when you look at BZ, you see some variations that are owing to the tilt of the dipole. And then this big okay, yeah, this big stuff here was the big Halloween event in 2003. So that's a CME. Bernie Jackson has done a lot of work on integrating different data sets, the IPS tomography. He's also looked at including SME, heliospheric imaging information, and combining this with models and tomography techniques. This is an example from him where he used a source surface model, the current sheet source surface model, and he's got in there a same kind of Parker spiral and Russell McFerrin. And when he integrates all these different data and he makes these assumptions, he can start to get agreement even for the field directions, which is very similar to what I was showing from WSA, just from the speed profile. And then Bernie has in here some density information that's coming from IPS, integrated with a and from all the different sources, the radio sources, and but he's also got these assumptions. And then I don't have this here, but Bernie has done a lot of work. You know, when he adds in SME data, he also gets better agreement. So we need a way to integrate the PUNCH data in with other data sources in order to get more valuable and more accurate products, and is knowing what's headed towards Earth. Okay, and this is an example where people were looking at tracking CMEs, and here they've got the excess density relative to the K corona, and so this is the CME here, and this is the amount of extra density that's in the CME direction, and they use the density as a function, the background density as a function of distance, to then also take this excess and add on the background, that radial trend in the density that I showed you from the solar wind statistics. And when they add it on, they get kind of a nice general agreement with the measured density at 1 AU for the CME. So these assumptions have already started to be used. Yeah, and then now I have the summary slide. And so, but I think that we can, we really are going to probably need, in order to look at what's headed towards Earth, we are going to need to integrate all these different sources, and then the solar wind statistics can play a key role in that. And that's it.
All right. Thank you very much, Heather, for that scene setting talk. And we will move on to Working Group 1B, Solar Wind Microstructures and Turbulence. This portion of our program will be introduced by Nicolene Weil, and she will introduce and hand off to the scene setting talk from Aleda Higginson. So are you ready to go? There she is. We have Dr. Weil's slides. Excellent.
Yeah, okay, let me do this thing. All right, I think everybody should be able to see the slides now. So thanks. Okay, thanks. All right, I'll go ahead and get started. Okay, so I'm going to play this beautiful stereo Core 2 movie over here on the right, just to wow you while I talk through some things. This is the Deep Field campaign that Stereo ran, just to give us a hint of what we think we might be able to see with PUNCH. So Working Group 1B determines how much and what types of mesoscale structures are solar in origin, and how much and what types develop and root from things like turbulence. Now, the careful listener will notice that I used the word mesoscale as opposed to microstructure. That's on purpose. Both of those words were chosen deliberately. Micro was chosen to emphasize how small these structures are relative to the standard ability to resolve things with stereo. For example, pushing the resolution limits of these stereo images. So micro was chosen to emphasize how small these are relative to the resolution. Physically, though, these are mesoscale structures, and I'll talk more about this dichotomy as we go through. Okay, so the reason we need to understand these structures is that, one, it provides critical insight into how and where kinetic energy becomes available to drive the turbulent cascade. Also, it's important to understand because all of this variability in density drives magnetosphere. We heard earlier Heather talk about storms from magnetic field fluctuations. The density is also important because the density is a dynamic pressure. It literally pushes on the magnetosphere. And so all of these structures that Punch is going to see can also have magnetic field that's important. The density alone is important for understanding the driving of the magnetosphere, both in terms of broadband power at ultra low frequencies and also discrete power at particular frequencies. Okay, let's talk about some of these scales and why we've been talking sometimes about micro and sometimes about meso. Turbulence, micro scales would really be down here in the dissipation range. And so that's why physically micro isn't the right word to use. And Bill Matthews pointed this out from the beginning. I've highlighted here the sort of a canonical 1AU turbulent spectra of the magnetic field. And it just shows the energy containing scales at the very low frequencies or long wavelengths. In the middle is the inertial range. And at the very, very high frequencies are the dissipation kinetic scale type effects. And I've just pointed out some relevant time scales. 8 minutes is there kind of in the inertial range. 20 minutes is pretty near to the spectral break. And then 100 minutes is way out in the energy containing scales for this particular trace of plasma. So that's just to give you kind of a metric, a ballpark of where we're at. Here's some other scales. On the left is that movie of the stereo core 2. And then the movie that I'm playing is a zoom in of the upper right quadrant. So this is a super zoom in of that already sort of high resolution movie. And that little blue dot is the Earth's day side magnetosphere to scale. So that just highlights the point that these things that are small compared to the resolution are actually large compared to Earth's magnetosphere. And really in the mesoscale sort of physical range. And this is why it's so important to understand these scales. It's because even these smallest things that we're seeing in the images are large and will drive dynamics in the Earth's magnetosphere. So just to give you some more numbers, 1 solar radii is 0.25 degrees. And the punch resolution for the NIFI, the inner requirement, is 3 arc minutes, which is about 140 megameters perpendicular to the line of sight if you're assuming plane of the sky. And that scale size, 140 megameters, advecting at sort of a slowish wind speed of 400 kilometers per second, that's about 6 minutes for that structure to advect past your pixel. So that's just to point out that the advected timescales are pretty well matched with the actual observing timescales that Punch is going to have. All right, so back to our science question. Our science question is to understand how much structure, mesoscale structure, comes from the sun and how much is formed en route through things like turbulence. And we already know from stereo and especially processed data with the heliospheric imager that both types of structures exist. So here is a series of co-moving high one frames illustrating both types of structures. The top row shows a structure that already existed near to the sun. Time advances from left to right. So the top row is an example of a structure that was there, it's still there. Keep going outwards in the co-moving frame and it's still there. The bottom 2 panels though, the bottom 2 rows are examples of co-moving frames following new structure that's being formed. The middle one is sort of an interesting kind of structure, and then you see that it totally changes and it evolves, and by the right-hand side, the further out, it's a totally new kind of structure. So clearly lots of dynamics, these flocculae patterns. And then the bottom row there's kind of nothing on the lower left. And then as you progress with the co-moving frame out to the right, then there's this little, what looks almost like a little CIR, a little compression region. So we know both types of structures exist. We want to know under what conditions each is created and how they interact with each other since they're both there. Here's a cartoon visualization to show this sort of mesoscale regime. This is from a paper that I put together with Craig DeForest and Larry Kepko. It's called Mesoscale Structures in the Solar Wind. It's under review right now in Frontiers, but we got really positive feedback from the reviewers. And so I expect it to be published pretty shortly. Anyway, this is a cartoon representation of some of this physics that we're talking about. On the left shows the scale sizes that we're kind of talking about at the top, very small kinetic dissipation type scales. In the middle is the mesoscales that we're focused on for this question 1B. At the bottom, it gives some illustrative large scale structures. So from left to right, on the left, we've listed just some cartoon representative phenomena. At the large scales, we've got things like CMEs and CIRs. We've got microstreams, floccula, streamer blobs, periodic density structures. Notice that the magnetosphere is small compared to most of these mesoscale structures. In the middle there, I've got this kind of representative spectral slopes. The large scale tend to be energy containing. Those mesoscales tend to be inertial, though there's a lot of variability in that. In the middle, you can see dominance. And what that means is the short scales, the kinetic scales, those evolve immediately. So everything that we see at those small scales are from evolving turbulence and interactions. Conversely, at the large scales, CIRs, coronal mass ejections, that's injected or imposed from the sun on these large scales. The mesoscales is this regime right in the middle where we've got the competition of both. There is stuff that is imposed and injected from the sun. And we're going to hear Aleda talk about some examples of types of structures that would be injected from the sun. But meanwhile, you've got turbulence making new structures and wiping those structures out. So there's a competition of both effects. And the observation tools show that there's a gap that we can't see a lot of this mesoscale structure. And this is just a cartoony way to show that PUNCH, because of its simultaneous high resolution with global coverage, fills in this gap so that we can resolve the individual mesoscale structures and also see how they map to the big global picture. So that's what that purple triangle is meant to represent. And so I just want to encourage more generally that PUNCH can embrace this opportunity to finally enable the understanding of the complex three-dimensional time dynamic solar wind, as opposed to having to use these oversimplified ways of discussing the solar wind. Okay, so just quickly, some of our measurement tools that we're going to use. We're trying to measure velocity, density, obviously, but the size scales and the locations of these structures. We're using tools like Fourier spectra, structure functions, autocorrelations, image deblurring, flow mapping, things like that. I want to say briefly that we are working closely with all of the other working groups because we want to understand the flows. We want to understand how our structures relate to the alpine surface, how they relate to CIRs and SIRs, things like that. And I'm just going to end on a plug for synergies, not just within PUNCH, but also externally with other missions and so forth. Things that we should be thinking about and are thinking about and hoping to talk about more this week are how PUNCH in general can relate to other white light imagers. Anytime the fields of view overlap, how we can be comparing. PUNCH to in situ collaboration so that we can really understand the relationship between density with velocity, temperature, and B field. Comparing with the in situ and L1 quantities at L1 to see geoeffectiveness of the structures. And then comparing with other remote imagers of lower down in the sun so we can compare to source regions. And then of course, models are so important. We're going to be hearing about that the rest of the session. And Aleda is going to be talking about one particular model next. That's what I have. Stop. Okay. All right, Aleda Higginson.
Aleda, I'll give you a 5-minute warning.
Okay, great, thanks. Can you all hear me?
Absolutely.
and see the right version of the slideshow? Okay.
Looks good.
All right. So as Nikki said, I'm going to be talking about one model in particular, which is the ARMS MHD code. And so as I was putting this together, I was really excited at the story we were able to tell by just using the one code ARMS. And I feel like there's a bad joke in there about punch and ARMS going hand in hand. But we're going to talk about how coronal magnetic reconnection can generate these solar wind structures that PUNCH will be able to see. So this is not to say turbulence is important. It's just not the language that I speak and not what I'm going to be talking about. And I want to point out that all of the simulations that I'm going to show have been done by this really awesome group of collaborators down here. So it's definitely not all my work. Okay. So first, some definitions. What you're going to hear me talk about a lot is the open-closed boundary or coronal hole boundaries. And I want to make sure to define this because it can mean different things to different people. So first of all, when you hear me say open magnetic field lines, that is basically where I'm talking about a field line that is connected at one end to the sun and at the other end to the solar wind. And so plasma is able to stream freely along this open field line and out into the heliosphere. The closed magnetic field lines are connected to the sun at both ends. And so they're trapping plasma in the corona, and so tend to be hotter, tend to have slightly different composition. So the idea is that you really would be able to see different plasma populations on open and closed magnetic field lines. The heliospheric current sheet is what separates the two coronal hole flux systems from either pole, if you're talking about a global dipole. So it is a boundary between open field lines out in the solar wind. And the coronal hole boundaries, so again, the open-closed boundary, this is where all of the really important magnetic reconnection that I'm going to be talking about is taking place. And it's a location where you can really have a drastic change in magnetic field topology. You can release plasma and you can create structures in the magnetic field, which you can then see in the solar wind. So observing these coronal hole boundaries is really important, and understanding where they map to in the heliosphere is also really important. And so the way that we typically talk about that to try to understand where these coronal hole boundaries are is we talk about the S-web or a separatrix web. But what I want you to take away is that when we talk about S-web, we're really just talking about the places out in the heliosphere where you're in purely open wind. You can be at 1 AU, you can be at Parker Solar Probe, wherever you are. If you are along an S-web arc, then you know that when you map that field line back down to the sun, then you are very near to an open closed boundary or a closed field region. And so you might expect that if you're in one of those if you're along one of those S-web arcs, that you would be seeing a lot of plasma dynamics and possibly plasma from the closed field. So we often make these S-web plots here. So on the top, this is a map for a given Carrington rotation of the coronal holes. So we have red and blue there representing the opposite polarity open field lines. And then the white are the closed field lines. And you can see, I don't know if you can see my mouse here, you can see that there are these coronal hole extensions, which really go to low latitudes. And it's these extensions that create these S-web arcs in the heliosphere. So this is a map of the separatrix web at 2.5 solar radii. You can see this really strong arc here where you have a polarity change. That's the heliospheric current sheet. That's one of the most important open closed boundaries in the heliosphere. And then we also have these really high, we have these high latitude S-web arcs, and these are resulting from pseudostreamers. And so I've kind of colored just crudely here in PowerPoint, the structures on the surface of the sun, the structures in the coronal hole boundary that are creating these S-web arcs here. And this is dynamic. So as the as the coronal holes evolve, the S-web evolves, and you can see that you can get quite a complex global structure in the heliosphere. So the simulations that I'm going to show are all done using the ARMS MHD code. This is a code that currently is housed at Goddard, and it is developed by Rick DeVore. Stands for the Adaptively Refined MHD Solver. It solves the 3D ideal MHD equations in spherical coordinates. And it has a few ways that you can set it up, but all the simulations that you'll see here, I want you to remember that they are fully time dynamic. They have a self-sustaining isothermal solar wind. So this is a fully time dynamic solar wind interacting with the magnetic field. And we utilize adaptive mesh refinement and numerical resistivity, which is a feature of ARMS. And so we're really able to do some high resolution stuff right at the boundary where the reconnection is important to understand. So what are the dynamics that we're talking about at the open-closed boundary? There are two main types of reconnection that it can occur there. These, the cartoon that you see there on the left is a paper from Wang et al. 2000. It's a figure from that paper, which proposes these as kind of the two main types originally. So you have heliospheric current sheet reconnection. That is also sometimes called helmet streamer pinch-off reconnection, where you have a large closed magnetic field loop, and the tip of it gets stretched out by the solar wind such that it comes together and actually reconnects with itself. And you have a disconnected, in 2D, a disconnected magnetic flux rope that then moves outwards into the solar wind and drags plasma with it. The other type is interchange reconnection, which is an inherently 3D process. So that's why we have to use solid and dashed lines here in the cartoon. And this is when you have an open and a closed magnetic field line, which essentially reconnect somewhere up at the top of the helmet streamer or the pseudo streamer, wherever it is that you're studying. And the field lines just switch foot points. And so the open field line becomes closed and the closed field line becomes open. And when that happens, you can release all of that plasma from the closed field. It's now on an open field line, it can just move out into the solar wind. And so on the right here, I've shown just two stills from simulations that we've done with ARMS, where we actually were able to simulate both of these processes happening dynamically. So on the right here, this pinch-off reconnection, all of these purple field lines that you can see coiled up here, these are 3D representations of this blob in the current sheet. And then this red field line here was closed, and you can see that it is now open, and all of the plasma that was on it is now able to spill out into the solar wind. So two types of reconnection and at least three ways to get these dynamics. So I'm going to show you a simulation that demonstrates each of these types. One is the global rearrangement of magnetic flux can lead to this type of both of these types of reconnection. The solar wind interaction with the top of helmet streamers, which is why it's so important that we have this time dynamic solar wind in our simulations. And then thirdly, photospheric motions, where we're really accounting for how motions down on the surface of the sun are wiggling and jiggling the magnetic field in such a way that it's causing reconnection and giving us these solar wind structures. So the first is the global rearrangement of flux. So this is a simulation done by Roger Scott, who's published this year, 2021, and his co-authors. And this is an idealized version of the types of things that might occur on much longer timescales on the surface of the sun. So what they did to simplify the process of this kind of global rearrangement that occurs just as the sun evolves during a given rotation period is they took a pseudo streamer and helmet streamer topology. So that's what you can see here on the right. We have global helmet streamers and then a pseudo streamer. You can see this much smaller dipole here. This black field, the black lines are the grids. You can see they have high resolution along the pseudo streamer structure. And here on the left, you can see the velocity field on the surface of the sun that they imposed. So we have this circulation here. So everything is moving up right here in the center. And this contour is showing you where the pseudostreamer structure is. And so what this velocity field does is it actually pushes the pseudostreamer northward, and it is originally in all of a closed field, and then by the end of the simulation, it's an open field. And so basically the question they were trying to answer is what happens if you push a pseudostreamer structure from the closed field into the open field? And the answer is you get a lot of interchange reconnection. The quote from the paper is copious amounts of interchange reconnection. And so here, these are some figures zoomed in on the pseudostreamer field line. So you can see here, this white field line is closed at the beginning. It passes very close to this null point that defines the top of the pseudostreamer. And then at a later time, this field line is now open, right? So these field lines that are passing through the null are open. And the yellow and purple there is showing you where you have high current density. And so that's showing you the location where the reconnection is happening. And so this interchange reconnection is something that would release density and closed field plasma into the solar wind. The second type of simulation that I want to show you is the interaction of the open closed boundary with the solar wind. So this is a simulation that Ben Lynch and I published in 2018, where we showed that the interaction of the solar wind with the helmet streamer is enough to produce flux ropes in the current sheet from pinch-off reconnection. So this is a callback to that still that I showed you at the beginning, where I was really describing how you can get pinch-off reconnection from a helmet streamer. And so this is, the movie you're seeing is a view top down, where you're looking at the heliospheric current sheet in this plane, and the black and white pairs each represent a magnetic field flux rope that is moving outwards into the solar wind, purely as a result of the fact that we have a solar wind dragging the top of the helmet streamer structure outwards and causing that pinch-off reconnection. And so the blue lines here are some sample field lines, just showing that this is a really dynamic process and that these structures can be quite interconnected with each other. And here is another view of that. Now, this is a close-up and a camera angle change of one of these flux ropes. And on the left, we have the simulated in situ data from this bead as the solar wind passes over it. And you can see how the connectivity that that bead or sample spacecraft is experiencing, how that connectivity changes as these structures pass over it. And you can see this nice rotation in the magnetic field, and we have a peak in the density as well. And the last type of oh, and I want to point out too, so staying on this, the pinch-off reconnection, Ben Lynch last year, the year of hell, managed to get a paper out demonstrating that these pinch-offs actually would result in coronal inflows or in and out pairs. So he did another simulation which showed the same process happening, the solar wind interacting with the helmet streamer, causing this pinch-off reconnection in these outflows. And he was able to actually show in the density these signatures of the corresponding magnetic field lines moving inwards and having a density signature going in as well. So this was the first time that we were able to show that in a simulation, which was really cool. So here, this is a plot where he's done these height time plots, and you can see for a few different locations, the upflows and the downflows moving together. The really interesting thing that he pointed out in the paper was that the viewing angle really mattered when you were looking for these, and the easiest time to observe them was when the viewer was actually looking at the current sheet rather than that nice edge-on view that we tend to think about where you have this global dipole and you're sitting at like Earth's orbit and looking at it edge-on. That actually turned out to be a really difficult orientation of which to view these structures. But when the current sheet was tilted because of an active region, then suddenly you're not looking through the entire current sheet, you're just looking through a piece of it. And that was when he was really able to pull these signatures out. So I think that's going to be a really important result for PUNCH. So the last type here is photospheric motions driving the open-closed boundary. And so now I want to highlight a simulation that's been done by Val Aslanyan and David Ponton, which is a collaboration at Dundee. And they simulated what happens when you drive a helmet streamer open-closed boundary and a pseudostreamer open-closed boundary with small-scale photospheric motions. So again, to give you an idea of the global topology on the left, we have a helmet streamer here. The heliospheric current sheet exists between these two blue field lines here, and you can see that we have pinch-off happening because of the solar wind. And then here, these field lines are showing the pseudostreamer structure that they simulated here. And then this is a view looking down onto the surface, showing you where the coronal hole boundaries are. So this is created using the squashing factor, which is this Q that we sometimes use, but I want you to focus, the thing I want you to take away from this is that the red-blue boundary is the open-closed boundary. That's the coronal hole boundary. And so the place where the driving is taking place is this lower latitude coronal hole, where the bottom along here is the helmet streamer boundary, and the top of this lower latitude coronal hole is a pseudostreamer boundary. I see I'm getting a time warning probably, so thank you very much. This is the last simulation. So here I'm just showing the motions where Val placed them on the coronal hole boundary. So again, in black, you see the open closed boundary, and all of these circles are where he put these super granular rotations out of phase to really try to mix up what the open closed boundary is doing right there. And you can see the effect of these rotations on that open closed boundary down here at the bottom. Again, so blue is all open field, red is closed, and you can see the boundary between them gets really mixed up. And the result of that is a lot of interchange reconnection. And so Val was able to actually map out into the heliosphere where you might see the result of this interchange reconnection. So these are contours at 20 solar radii. The orange here are field lines that are completely disconnected from the sun. So these are these heliospheric current sheet blobs. This is the location of the current sheet here. And then the gray regions on the left, this is when he drove the helmet streamer, and on the right, this is when he drove the pseudostreamer. The gray regions are everywhere where the field line has experienced interchange reconnection. And so it was closed and now it's open. And if a spacecraft were to fly through those regions, it would be observing flux, possibly from a previously closed field region. So this is my last slide, and I just put those three ways to get the two types of dynamics again. Again, the global rearrangement of magnetic flux, the solar wind interaction with the tops of helmet streamers, and these photospheric motions. And then I put some notes down here on what would the signatures in the solar wind be, specifically thinking about PUNCH. So for sure, the density enhancements, as Nikki mentioned, that's so important for driving the magnetosphere, something that PUNCH will be good at measuring. And importantly, the viewing angle, the orientation between the heliospheric current sheet and the spacecraft is probably going to be really important for that. It's important to think about the magnetic structure because you can get different types of structure from whether you're looking at a helmet streamer or a pseudostreamer. I put question marks there for alphane waves because there are some simulations that show maybe you would get them and some that show that maybe you wouldn't. So that's really an open question still. And then, of course, all of the signatures that were associated with the originally closed field plasma. And so that's kind of what we used to call slow wind. And hopefully we're moving away from that dichotomy of fast and slow wind, but things like plasma composition, electron straw, dropouts, all of that. So thank you very much. And happy to take questions and the discussion session if that's appropriate. Thanks.
Thank you, Dr. Higginson. So I want to remind everyone, we have a break on the schedule. Please try to connect to Slido. The link, the most recent link in the chat has been provided, and there shouldn't be any barrier to entry. This will conclude session 1, talks regarding working group 1 and 1A and 1B. And the next session will be a plenary free discussion where any questions that you've entered can be discussed. That will be moderated by Barbara Thompson and Nikki Weil. And so take advantage of the break to perhaps get into Slido, ask for tech support if you need it, pose any questions there. This will really help us document the intellectual exchange instead of the random comments in the chat. So please click on that link that Calvin Tavares has put in there. It should be no barrier to entry. And if there is, go ahead and write to him and he'll help you use this simple system. So we will break for the next 10 minutes, unless Sarah or Craig, you want to give a full 15 minutes and let the schedule slip by 5 minutes. Could you comment on that?
Craig, do you want to comment?
Sure. At this point in the day, given that we have all the discussions ahead of us, if folks are okay with 10, let's stick with that.